Hello, my dear students, and welcome. So, today we're tackling a very important topic from your first chapter, the electric field. I know it can seem a little bit abstract, a little confusing maybe, but please don't worry. We're going to break it down in such a simple way that you'll not only get the concept, but also be completely ready for your exams. Shall we start?
All right, let's get right into it. Now, we all know from Coulomb's law, right? Two charges can push or pull each other. A positive charge will repel another positive charge. But they do this without ever touching. They can be separated by completely empty space, by a vacuum, and still, that force is there. Now, isn't that a little bit strange? It's a puzzle. How does this action at a distance even work? Just think about it for a second. If you have one charge sitting here and another one way over there, how does the first one send a message to the second one saying, "Hey, I'm here, you need to move"? How is this information, this force, being sent across empty space? It's a wonderful question, and it's really at the heart of what we are going to learn today. Well, the answer isn't some kind of magic. It's actually one of the most powerful and beautiful ideas in all of physics. The answer is the concept of a field. For us, today, it's the electric field. And this one idea, it just unlocks everything.
So, what is this electric field exactly? I think the best way to understand it is with a simple analogy from our everyday life. Let's just forget about charges for 1 minute, okay? And think about something we all know. Imagine you're sitting near a campfire. You can feel the warmth, right? On your hands, on your face. But you're not actually touching the fire. So what's happening? The fire has changed the space around it. It has created a zone of influence. You could call it a heat field. And anywhere you go inside this field, you're going to feel that heat. Now, an electric charge does exactly the same thing. A source charge, let's call it capital Q, it modifies the space all around itself. It creates an invisible region of influence. And this influence, this modification of space, is what we call the electric field. It becomes a property of the space itself, all because that charge is sitting there. Okay, so here is the most important part, the real trick. When you bring a second, smaller charge, we'll call it a test charge, little q, into this region, the two charges don't interact with each other directly. No, that test charge Q interacts with the field that is present at its exact location. You see? The field is the middleman. The field is the one that actually exerts the force on the second charge. A good way to remember this is the field is the cause, and the force that the charge feels, well, that's the effect.
Now, that's a really good way to get the feel of the concept. But this is physics, and for your exams, we need to be very precise. We need a proper definition, we need to be able to measure it, to calculate it. So let's look at the formal definition straight from your NCERT textbook.
Please pay very close attention to this wording. This is exactly what you should write in your exams if you want full marks. The electric field at any point in space is simply the force that a unit positive charge, meaning a charge of +1, would feel if you put it at that exact point. It's nothing but the force per charge at any location. And this definition gives us a very simple formula. The electric field, which we call E, is equal to the force, F, divided by the test charge Q. So E is F over Q. Simple. And from this formula, the unit becomes very clear also. Force is in newtons and charge is in coulombs. So the unit for electric field is newtons per coulomb, N/C. Easy, isn't it? So how do we actually calculate the strength of this field made by just one source charge Q? Well, it's a simple three-step process. First, you identify your source charge, Q. Second, you pick the point in space where you want to know the field strength, which is at a distance r away. And third, you just have to apply the formula. E equals kq divided by r squared. This formula, by the way, comes directly from Coulomb's law. Let's do a very tiny example to make this super clear. Let's say, what is the electric field 1 meter away from a positive 1 Coulomb charge? Okay, we just put the numbers into the formula. K is 9 into 10 to the power of 9. Q is 1 and R is 1. So E equals 9 times 10 to the power of 9 times 1 all divided by 1 squared. The answer is simply 9 into 10 to the power of 9 newtons per coulomb. See, the formula is actually very easy to use. Now remember, electric field is a vector quantity. That means it has a direction. So, what is its direction? Just go back to the definition. It's the direction of the force on a positive test charge. So, if your main source charge is positive, it's going to push a positive test charge away from it, right? So the field points outwards. And if your source charge is negative, it's going to pull a positive test charge towards it. So the field points inwards. It's that simple.
Always outwards from positive and always inwards towards negative.
Okay, now for a very, very important point. This is something where many students get confused and they end up losing marks in the exam. We need to be absolutely 100% clear on the difference between the electric field and the electric force. They are related, yes, but they are not the same thing at all.
Let's look at this table to make it crystal clear. First point, who creates it? An electric field, E, is created by just a single charge, but an electric force, F, is an interaction between two charges. This means a field can exist all by itself, even with no second charge around. Now look at the formulas. The field, E, depends only on the source charge, Q, but the force, F, depends on both charges, Q and Q. And finally, look at the units. They are different. Newtons per coulomb for the field, but just newtons for the force. Please, beta, remember this difference. It's a very common place to make a mistake.
Okay, so we've covered the main idea, the formal definition, the formula, and we've also cleared up a very common confusion. So let's just quickly summarize the most important points you need to remember for your exam. Let's recap. First, any charge creates an electric field in the space around it. Second, it is this field that exerts a force on any other charge that comes nearby. Third, the definition is simple. Force per unit positive charge. E equals F by Q. Fourth, the direction. Outwards from positive, inwards toward negative. And fifth, a great way to remember it, the field is the cause and the force is the effect.
You might be wondering, sir, why is this idea so important? Well, because the concept of a field is truly one of the main pillars of modern physics. It doesn't just explain how static charges push and pull each other. This exact same idea of a field is what will later help you understand magnetism, light, radio waves, even X-rays. They are all just different types of fields moving through space. So understanding this properly now builds the foundation for so much that is going to come later.
And that leads me to one last fascinating question for you to think about. We said the electric field is like a messenger, carrying the news of the force from one charge to another. So if one charge suddenly moves, the field around it has to change, and that change has to travel outwards to tell the other charges. But how fast do you think this message travels? Is it instant, or does it have a speed limit? It's something to think about. And we'll find the answer to that when we study electromagnetic waves. Thank you for